Welcome back, class. Today's lecture is lecture 7, Control of Microorganisms by Physical and Chemical Agents. So in this lecture we'll be focusing on the control of microbes, but keep in mind that there are lots of mechanisms used to control microbes that are not covered in this lecture. So for example, the manipulation of environmental conditions is used extensively in the food industry to preserve foods. Increased solutes such as sugar and salt are used to preserve meats and jams, for example. Microbial fermentations of milk and vegetables decrease the pH of these foods, and this creates new foods such as yogurt and cheese and so on, and all of these have a longer shelf life than the milk and vegetables from which they're made. Heat and the generation of anoxic conditions are also important in preserving canned foods, and ionising radiation is used to extend the shelf life of seafood, fruits and vegetables. So physical agents are generally used to sterilise objects. Chemicals, on the other hand, are more often employed in disinfection and antisepsis. So the proper use of chemical agents is essential. Chemicals are also employed to prevent microbial growth in food, and certain chemicals are used to treat infectious disease. Now, there are many different chemicals available for use as disinfectants, and each has its own advantages and disadvantages. So in selecting an appropriate agent, it's important to keep in mind the characteristics of a desirable disinfectant. Ideally, it should be effective against a wide variety of infectious agents, that is both gram-positive and gram-negative bacteria, bacterial endospores, fungi and viruses. Should be effective at low concentrations and in the presence of organic matter. Although the chemical must be toxic for infectious agents, it should not be toxic to people or corrosive for common materials. In practice, this balance between effectiveness and low toxicity for animals is very hard to achieve. Some chemicals are used despite their low effectiveness because they're relatively non-toxic. The ideal disinfectant should also be stable upon storage, odourless or with a pleasant odour, should be soluble in water and lipids for penetration into the microorganisms, should have a low surface tension so it can enter cracks in surfaces, and be relatively inexpensive. So we're going to look at the properties and uses of several groups of common disinfectants and antiseptics, and you can see the structures of some of the common agents shown here, and you'll be familiar with many of these from living systems too. So as you can see, we've got these different major groups here: the phenolics, alcohols, halogenated compounds, aldehydes, quaternary ammonium compounds and gases. Let's start with the phenolics. Phenol was the first widely used antiseptic and disinfectant. In 1867, Joseph Lister used phenol to reduce the risk of infection during surgery. Today, phenol and phenolics, which are phenol derivatives, such as cresols, xylanols and so on, are used as disinfectants in laboratories and hospitals. The commercial disinfectant Lysol is made of a mixture of phenolics, and phenolics act by denaturing proteins and disrupting cell membranes. They have some real advantages as disinfectants. They're very effective in the presence of organic material, and they remain active on surfaces long after they've been applied. However, they have a disagreeable odour and can cause skin irritation. One example pictured here is hexachlorophene, which has been one of the most popular antiseptics because once applied, it persists on the skin and reduces skin bacteria for long periods of time. However, it was found to cause brain damage and is now only used as a last resort and in response to a staphylococcal outbreak. The alcohols, these are among the most widely used disinfectants and antiseptics. They are bactericidal, fungicidal, but not sporicidal, although some viruses are also destroyed by alcohols. The two most popular are ethanol and isopropanol, normally used at a concentration of about 70 to 80%. The alcohols act by denaturing proteins and possibly by dissolving membrane lipids. A 10 to 15 minute soaking is usually sufficient to disinfect small items. The halogens, you'll remember from Living Systems 1, halogen is any of the 5 elements fluorine, chlorine, bromine, iodine and astatine found in group 7A of the periodic table. They exist as diatomic molecules in the free state, and the most important antimicrobial agents out of this group are iodine and chlorine. Let's look at the halogen iodine. Iodine is used as an antiseptic and it kills microorganisms by oxidizing cell constituents and iodinating cell proteins. In other words, combining with proteins and inactivating them. At higher concentrations, it may even kill some spores. Iodine often has been applied as a tincture of iodine at 2% or more in a water ethanol solution. And although in this manner it's an effective antiseptic, it may damage the skin, it leaves a stain, and iodine allergies can result. So more recently, iodine has been complexed with an organic carrier to form what's called an iodophore. Iodophores are water soluble, they're more stable, they're non-staining, and they release iodine slowly to minimise skin irritations. Here's our next halogen, chlorine. This is the normal disinfectant for municipal water supplies, swimming pools, but it's also employed in the dairy and food industries. It can be applied as chlorine gas, sodium hypochlorite, which is just bleach, or calcium hypochlorite. And all of these yield hypochlorous acid and then atomic oxygen. The result is oxidation of cell materials and destruction of vegetative bacteria and vegetative fungi, although not spores. Death of almost all microorganisms usually occurs within 30 minutes. But since organic material interferes with chlorine action by reacting with chlorine and its products, an excess of chlorine is added to ensure complete microbial destruction. Another potential problem with chlorine is that it reacts with organic compounds to form carcinogenic trihalomethanes, which have to be monitored in drinking water. Ozone has sometimes been used successfully as an alternative to chlorination in both Europe and Canada. Chlorine is an excellent disinfectant for individual use because it's effective, it's inexpensive, and it's easy to use. Small quantities of drinking water can also be disinfected with what are called halazone tablets. Halazone slowly releases chloride when added to water and disinfects it in about half an hour. This is frequently used by campers who lack access to uncontaminated drinking water. Chlorine solutions also make very effective lab and household disinfectants. A very good disinfectant detergent combination can be prepared if a 1 in 40 dilution of household bleach is combined with a non-ionic detergent, such as dishwashing liquid, to give a 0.8% detergent concentration. And this mixture will remove both dirt and bacteria. What about the use of heavy metals? For many years, the ions of heavy metals such as mercury, silver, arsenic, zinc and copper were used as very effective germicides. But these have now mostly been superseded by other less toxic and even more effective germicides. There are still a few exceptions. In some hospitals, a 1% solution of silver nitrate is still used as an eye treatment. Silver sulfadiazine is still used on burns. Copper sulfate is still used as an effective algicide in lakes and swimming pools. Heavy metals work by combining with proteins, often with their sulfhydryl groups, and inactivating them. They may also precipitate cell proteins. Quaternary ammonium compounds. These are detergents that have antimicrobial activity, and they're very effective disinfectants. Detergents are simply organic cleansing agents that are amphipathic. That is, they have both polar hydrophilic and non-polar hydrophobic components. Here we have the hydrophilic portion of 2 quaternary ammonium compounds, and that contains a positively charged quaternary nitrogen. So quaternary ammonium compounds are cationic detergents, and their antimicrobial activity results from their ability to disrupt microbial membranes. They may also denature proteins. Cationic detergents will kill most bacteria, but not endospores. They have the advantage of being stable. They're also non-toxic, but they are inactivated by hard water and soap. Both of the commonly used aldehydes are shown here, formaldehyde and glutaraldehyde. Both of these are highly reactive molecules which act by combining with nucleic acids and proteins and inactivating them. They are highly effective. They are sporicidal, and they can be used as chemical sterilants. Formaldehyde is usually dissolved in water or alcohol before use. Glutaraldehyde is normally used as a 2% buffered solution, and this is quite an effective disinfectant. Glutaraldehyde is less irritating than formaldehyde, and it's used to disinfect hospital and laboratory equipment. Glutaraldehyde can disinfect objects within about 10 minutes, but may require as long as 12 hours to destroy all endospores. Testing of antimicrobial agents often begins with an initial screening test to see if they're effective and at what concentrations. This may then be followed by more realistic in-use testing. The best known disinfectant screening test is the phenol coefficient test, in which the potency of a disinfectant is compared with that of phenol. First, a series of dilutions of phenol and the disinfectant being tested are prepared. Standard amount of Salmonella typhi and Staphylococcus aureus are added to each dilution. The dilutions are then placed in a 20 degrees or 37 degrees water bath. At 5-minute intervals, samples are withdrawn from each solution and then used to inoculate a growth medium, which is incubated for 2 or more days and then examined for growth. If there's no growth in the growth medium, the dilution at that particular time of sampling killed the bacteria. The highest dilution, that is the lowest concentration, that kills the bacteria after a 10-minute exposure, but not after 5 minutes, is used to calculate the phenol coefficient. This is done by dividing the reciprocal of the appropriate dilution for the disinfectant being tested by the reciprocal of the appropriate phenol dilution. For example, if the phenol dilution was 1 in 90 and the maximum effective dilution for disinfectant X was 1 in 450, then the phenol coefficient of X would be 5. The higher the phenol coefficient value, the more effective the disinfectant under these test conditions. So you can see here that the value given to phenol is 1. So a value greater than 1 means the disinfectant is more effective than the phenol. A few representative phenol coefficient values are given in this table. So it's interesting to see that the second disinfectant listed here, acetylpyridinium chloride, which is a quaternary ammonium compound, has a very, very high phenol coefficient value of 228 for Salmonella and 337 for Staphylococcus aureus. Another interesting example, the second last disinfectant on this list, ethanol, has a low phenol coefficient value of 0.04. So the phenol coefficient test is a useful initial screening procedure, but it can be misleading if taken as a direct indication of disinfectant potency during normal use. And this is because that value is determined under carefully controlled conditions with pure bacterial strains, whereas disinfectants are normally used on complex mixed populations in the presence of organic matter and with significant variations in environmental factors like pH, temperature, and the presence of salts. So to more realistically estimate disinfectant effectiveness, other tests are often used. The first one listed here is the use dilution test, and this determines the rate at which selected bacteria are destroyed by various chemical agents. Disinfectants also can be tested under conditions designed to simulate normal in-use situations. This in-use testing allows a more accurate determination of the proper disinfectant concentration for a particular situation. And this is one test that we'll be using in prac class. This table summarises the activity levels of some selected germicides. Note that an activity level rating of high means that the germicide will destroy all vegetative cells as well as bacterial endospores. A rating of intermediate means that the disinfectant will destroy all vegetative cells but not endospores. And an activity level rating of low means that the disinfectant will kill most vegetative cells but not bacterial endospores or small non-lipid viruses. And finally, I would like to leave you with this table, which summarises many of the characteristics of commonly used disinfectants and antiseptics.